This meeting is being recorded.
In the next section of the chapter on chemical kinetics, we're going to review what's referred to as a reaction mechanism. So a reaction mechanism, in simplest terms, is the sequence of events that describes the actual process by which reactants become products. So we might be familiar with reactions going from products or reactants to products, but it seems like it only happens in one step, the way that we look at most reactions. But in reality, reactions may occur all at once or through several discrete steps. These discrete steps are referred to as the elementary reactions. So we can describe the molecularity of these elementary reactions based on how many molecules are reacting to produce products, or how many molecules the rate depends on to produce a product. So we have a unimolecular molecularity when only one reactant turns into a product. And we can relate the rate law in that case to be something like this over here, where we have the rate is equal to some constant K times the concentration of our analyte here. When we have a bimolecular process, we could either have one single reactant that has to, or two of the same reactant rather, that have to react, and then we would see a rate law here depends on the concentration of A squared, since this is a bimolecular process, or we could have bimolecular processes where two different reactants control the rate. So that's what we see here in that last box. So the molecularity, again, tells us how many molecules are involved in each of these processes. So each elementary step. When we have a multi-step mechanism, we can add all of the elementary steps together to give us the overall reaction, overall process. And after one step is completed and then a second step begins, if something is produced in one step and then consumed in a subsequent step, we call that species an intermediate. So we'll take a look at sample exercise 2 here, and we'll actually see an intermediate. So we're given this proposed mechanism for the conversion of ozone into O2. So that's what we see over here. We see our reactant ozone, and then that produces in our first elementary step, a diatomic oxygen, O2 gas, and O. So that's the first elementary step. And then we have a second step here, which ozone, again, is our reactant, but now it reacts with the one of the products that was produced in the first step. So we can actually cancel these out in a sense, just like we did when we talked about net ionic reactions. These intermediates will not be part of our overall reaction. So we'll keep that in mind for part B. In part A here, we're asked to describe the molecularity of each of these elementary reactions in the mechanism. So step 1, we would describe this as unimolecular, because as you see, only one molecule is involved in this process. Let's see, in the second step here, we have 2 molecules. So this will be considered bimolecular. So again, we have one reactant, and here we will have 2 reactants. All right, so that answers part A. Now, if we were to write the overall reaction, we have to kind of add these 2 steps together here. So I'll make a little more room. So what we see, we have O3 gives us O2 plus O, and I'm leaving off the phases just for simplicity. Then we have O3 again plus O, and that gives us 2O2. So we're going to add these together just like a math problem here, and we're going to see that our overall reaction is 2O3. We'll cancel out that oxide, that O, and then we have this yields 1, 2, 3, O2. So this here is our overall equation, or the equation for the overall reaction. In the last part of this question here, we're asked to identify any intermediates, and we can say that O by itself, monoatomic oxygen is another way of saying that. So we'll take a look at the rate determining step next when we talk about mechanisms. And this is the slowest step in a reaction mechanism. So your reaction cannot go any faster than this rate determining step because this is the slowest step. So we see down here, if we have two scenarios here where toll plaza A seems to be moving slower over here than toll plaza B, we would say that this would be our rate determining step. It's the slower of the two steps. Whereas in the image down below, we see that toll plaza B is slower. So this would be our rate determining step over here. Again, the reaction cannot progress any faster than the slowest step. So depending on the rate of these steps, that would be how fast a reaction can actually occur.